Namaste and welcome back to Pal Talk Machine Learning. I'm your host, Dr. Chinmoy Pal, and today we're diving into the world of high-dimensional data visualization with a powerful technique called TSNE, or, in full form, T-Distributed Stochastic Neighbor Embedding.
And I'm Via. If you've ever looked at a dataset with hundreds or even thousands of features, you'll know how challenging it is to visualize patterns or clusters. That's why TSNE comes into the picture. It helps us project high-dimensional data into 2D or 3D while keeping local structures intact.
What is TSNE? So, what exactly is TSNE? It's a non-linear dimensionality reduction technique especially used for visualizing complex datasets. It was introduced by Lawrence van der Marten and Geoffrey Hinton in 2008. Yes, the same Hinton who's called the godfather of deep learning.
The basic idea behind TSNE is simple. It tries to ensure that data points that are close together in high-dimensional space also remain close in low-dimensional space. In other words, similar things still together, making clusters more obvious when plotted.
How does TSNE work? Let's simplify the math part. TSNE first calculates the probability that a data point chooses another as its neighbor, based on how close they are in high-dimensional space. Then, it does the same in low-dimensional space.
It then minimizes the difference between these two sets of probabilities using a cost function based on something called Kullback-Leibler divergence. And instead of normal Gaussian distributions, it uses a student's t-distribution in the low-dimensional space, which helps prevent crowding of points in the center.
Why use TSNE? You might ask, why not just use PCA? Good question. PCA is linear. It preserves global structure but may lose out on local relationships.
TSNE, on the other hand, captures local clusters and relationships beautifully, which is why it's very popular for visualizing outputs from neural networks, gene expression data, handwritten digits like MNIST, and more.
Parameters you must know. When using TSNE, you'll often come across three key parameters. Perplexity controls the number of effective neighbors, typically between 5 and 50. Learning rate, too small or too large, can lead to poor embedding. Number of iterations. Higher iterations help achieve stability in layout.
But remember, TSNE is computationally expensive, and it's not good for very large data sets unless you use optimized versions like Barnes-Hut TSNE or OpenTSNE.
Real-world applications. Here's where TSNE really shines. Bioinformatics, gene expression pattern visualization, image processing, clustering handwritten digits like MNIST, NLP, visualizing word embeddings like word-to-vec or BERT, deep learning, visualizing layers of neural networks to check how models are learning.
Even in marketing or finance, it's used to understand customer segmentation and behavior in a more visual way.
Limitations of TSNE. Now, TSNE isn't perfect. One major drawback is that it's only meant for visualization, not actual feature reduction for downstream models.
Also, the results can be non-deterministic, meaning if you run it multiple times, you might get different plots unless you fix the random seed.
And importantly, TSNE distorts global distances. So if two clusters look far apart in 2D, they might not be that different in high-dimensional space. Final takeaway.
To wrap up, TSNE is like magic for the eyes. It takes complex, high-dimensional data and makes it understandable and visually insightful, especially for exploratory data analysis.
But use it wisely. It's great for pattern discovery, but not for predictive modeling. And always pair it with domain knowledge for best results.
That's all for today's episode on TSNE. We hope you enjoyed this journey into data visualization.
Don't forget to follow Pal Talk Machine Learning on Spotify or wherever you get your podcasts. Until next time, keep exploring, keep learning.
And stay intelligent with your data.